Nowadays, more and more people trust science and its achievements. Take, for example, this last year. Shocked by the diffusion of COVID-19, the entire world is orientating its decisions according to what scientists are discovering. If we skip to the past, the situation was very different. Science wasn't so developed like today, and people used to not believe in everything experts were saying. Think, for example, to the Greek belief in fate. The transition between these two opposite views on life has happened somewhere between the 18th and 19th century, the period of Illuminism and determinism. This revolution of human thoughts and lifestyles has certainly brought to a great technological progress that continues until now. Many conclusions made in that era are totally wrong. Trusting the scientific method is the right thing to do, but posing all our hopes in science and thinking that everything can be predetermined through mathematical equations is an inaccurate reasoning that comes from Illuminism. As a matter of fact, some great discoveries made at the beginning of the last century unveiled a secret, totally and counterintuitive behavior of nature. I'm talking about quantum mechanics, particularly about Heisenberg's uncertainty principle, a shocking result that has changed completely our way of thinking about practically everything in this world. The whole 20th century was affected by this discovery, which totally destroyed our previous vision of science, which was characterized by determinism. Hundreds of poets and writers had been influenced by the revolution of quantum mechanics. But what is it about? Who was Heisenberg? What is his principal state? And why did it have so many consequences, even on different fields such as literature and philosophy? These questions are the topic of this video, so if you're interested, stick with me and prepare to this incredible journey in quantum mechanics. The Heisenberg principle is amongst the most pivotal ones in physics, and it hasn't been violated in any possible experiment. In few words, it states that it's not possible to measure both position and momentum of a particle with infinite precision. The product of the errors in the measurement of these two quantities must be higher than a constant value. The result is that if you know where a particle is, you ignore its velocity, and vice versa. Unfortunately, as you can imagine, it's not easy to understand why this principle works, so we'll firstly try to look at what physicists thought before the development of quantum mechanics. Given these bases, we'll then go through the uncertainty principle, and we'll try to understand why it's so in contrast with the previous theories. What was physics like before the 20th century? Well, many things can be said, but to start our description, we need to start from Newton. Known as one of the 3 or 4 most brilliant scientists ever, Sir Isaac developed what is recognized as classical mechanics, together with other famous studies on optics and obviously about gravity. What are the main principles of this theory? The first one is the law of inertia. If a body is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at a constant speed unless it is acted upon by a force. The law of inertia was first formulated by Galileo for horizontal motion on Earth and was later generalized by René Descartes. The second one is probably the most famous equation of physics, and it states that the force acting on an object is proportional to its acceleration through the mass of the object itself. F is equal to ma. The third is not relevant in this case, but it's always necessary to be remembered. If an object A exerts a force on object B, then object B must exert a force of equal magnitude and opposite direction back on object A. Another major achievement made by Newton and his subsequent colleagues was the development of mathematical calculus. Derivatives and integrals are strictly linked to classical mechanics. Even if we'll not go deep into this subject, it's necessary to underline the fact that mathematical tools can be used to find the velocity and the position of a moving body, starting from its acceleration. What is the consequence of all I've said? Well, if we're able to calculate the mass of an object and the force exerted on it, it's possible to derive the acceleration through Newton's second law, and then mass will provide us its velocity and the position depending upon time. This is totally deterministic model. As a matter of fact, Illuminism was powered by the discoveries made by Newton about physics. However, physicists of that period knew that many phenomena were not explicable to this classical theory. But when major discoveries were made in the 19th century regarding electricity and magnetism, the idea that everything could be determined by science drastically raised. In fact, physicists like Maxwell and Faraday understood that electricity and magnetism were two sides of the same coin. They elaborated the electromagnetic theory that stated the existence of electromagnetic waves. Furthermore, all of the optics studied in the previous centuries was just a consequence of the four Maxwell equations that governed electromagnetism, because light was just a particular type of an electromagnetic wave. What was the consequence of all this? Almost every phenomenon on Earth can be totally explained with gravity, classical mechanics, or electromagnetism. It was the apex of determinism. Therefore, in the 20th century, physicists understood that to explain this behavior of atoms, it was necessary to completely change the way of thinking about the world. It was necessary to abandon determinism. Classical theories weren't able to explain why we exist, since they predicted that medium of life of an atom was just around some fraction of a second. Totally incorrect. To better describe a particular phenomenon called Photoelectric Effect in 1904, Einstein stated that the light is quantized in small packets of energy called photons. In some cases, waves can be treated as particles with discrete values of energy. More precisely, each photon has an energy proportional to its time frequency through a constant called Planck's constant. After that, in 1924, the famous Louis de Broglie tried to invert this correlation. He proposed that all particles could be considered also as waves with a wavelength equal to Planck's constant divided by its momentum, which is just the product of mass and velocity. So, the higher the momentum of the particle, heavy or fast objects, the shorter the wavelength. In talking about waves, we must mention Fourier's transforms. Who invented this mathematical powerful tool? Well, it was elaborated by a French mathematician called Jean-Baptiste Joseph Fourier. After having fought in the French Revolution, he attended the École in Paris and followed the lectures of great teachers like Pierre-Simon Laplace and Joseph-Louis Lagrange. But wait a moment. What is a Fourier transform? Don't worry, we won't dive deep into the mathematical tools used in this topic, but we'll just try to have an intuitive idea of what it is. Fourier transform of a light wave is the distribution of the components of its time frequency. The principle is that all functions can be reproduced by a continuous infinite sum of waves with different frequencies. That, for experts, is an integral. Each frequency component has a weight that is established by the Fourier transform. For example, the transformed of a solar ray will have a peak on orange frequencies and decreasing values for other colors. Similarly to this, Fourier transform of a particle wave will be a distribution of spatial frequency is proportional to momentum thanks to de Broglie's hypothesis. So the Fourier transform is able to change our perspective regarding the particle from position to momentum. Even if we won't deal with the mathematical expression of this topic, we must underline its most important properties. If the function of which we calculate the transform is defined on every possible position, its Fourier transform will be limited to a discrete collection of frequencies. On the other hand, if the function is limited in a region and zero elsewhere, its transforms will be continuous and the function will be composed of an infinite number of frequencies. Think, for example, of an ideal yellow light ray that travels from minus infinite to plus infinite. He will be composed just of a spike on one single frequency correspondent to the yellow color, with the subsequent discrete Fourier transform. But what happens if our light ray is only existing in a region and zero elsewhere? Well, the transformed will always have a peak on the yellow frequency, but it must be composed of other waves that can zero the amplitude in all other regions of space, so the transformed would be continuous. You can naturally reuse the same considerations with a wave particle like the ones theorized by de Broglie. The smaller the spatial distribution of the function we want to transform, the broader the distribution of momentum will be. Are you following these concepts? We're very close to our final result, which is the Heisenberg uncertainty principle formulated in, but to have a good intuitive idea of why it works, we need to introduce one last thing. Root mean square error. What is it? Well, practically speaking, it's the uncertainty of the measurement of a physical quantity. For example, if the root mean square error is very low, our precision will be high. To have a very simplified idea, if a Fourier transform representing the momentum is broader, the error regarding its value will be bigger. Usually, physicists work their entire life on building appropriate devices that can reduce this error in order to obtain better results in their experiments. Hundreds of books have been written on this topic, but when it comes to quantum mechanics, it's not possible to use tricks to reduce the error. There's an inferior limit under which we can't go. Why? Because if we're measuring the parameters of a particle and we deal with its wave trying to make a narrower spatial distribution, the relative momental distribution, that is the Fourier transform, will become broader and vice versa. This is the content of Heisenberg's uncertainty principle, which is one of the most important postulates of quantum mechanics. We derived it from not rigorous wavy considerations, but from its true formulation comes from more advanced mathematical theories that we won't examine in this video. Just to be more precise, here's the rigorous definition. The product of the uncertainty in the position and the momentum must be higher than half the reduced Planck constant, which is the Planck constant divided twice by pi. So if we try to reduce the root mean square of position to 0, understanding where the particle is, the uncertainty of the momentum will go rapidly to infinite and vice versa. This result is at the same time extraordinary and terrifying. It's totally a different way of thinking about physics. Nature itself, which can be considered as made by quantums that are both particles and waves, prohibits us to measure everything with infinite precision. We can't calculate the exact trajectory of a particle. We must limit to say that there's a certain probability to find an object in a region. It's the death of Newtonian's determinism. Yes, science is really powerful, but it's science itself that has discovered that not everything can be predicted using maths, and how we can only limit ourselves to calculating probabilities. Something we can certainly manipulate well, but also something that is not so distant from the Greek fate we were talking about at the beginning. So are you amazed by quantum mechanics? Did you already know Heisenberg's uncertainty principle? Do you want to know more about wave-particle duality? Have you ever heard about Fourier? Let me know in the comments below.